Hello, welcome to Project 2.4 ISP Medium Fast Fourier Transform Spectrum Analyzer. On screen, you are seeing a spectrum analyzer. This was the intended final product for this ISP. However, unfortunately, I did not finish building my spectrum analyzer with a fast Fourier transform completely in hardware. We can see a demonstration of how the fast Fourier transform works because the microphone serves as the audio input and is displaying a magnitude frequency graph as the output. This is as far as I got on the breadboard prototype. So far, it's 10 breadboards, but due to me running out of a chip and the sheer complexity and size of the breadboard, I decided to discontinue with the breadboard prototype and focus mainly on the concepts and principles of the Fourier transform and spectrum analyzer. I will now be presenting an explanation of the Fourier equation and how it works. If I play a chord on a piano, how does the computer figure out which notes are inside it? That's exactly what the Fourier transform does. It takes a signal and breaks it down into frequencies. The FFT takes a set of samples, in this case 256, and converts them from the time domain into the frequency domain. Instead of asking what is the signal doing over time, it asks what frequencies make up this signal. Each frequency bin acts like a test wave. For a given bin, k, we generate a wave that completes k cycles over the 256 samples. We then compare this test wave to the signal. In this demonstration, we have a signal with a frequency of 2. Additionally, I have n number of samples represented in green here, and I have k, a variable which controls how fast each sample is rotated around the circle. As k increases, each sample is rotated by a larger angle, so the points move around the circle more quickly. When k does not match the signal frequency, the points spread out around the circle. Because they are spread out evenly, they cancel out, and the center of mass stays near zero. The reason that they don't appear to spread out evenly is because this center of mass is only analyzing the x portion of these samples. In reality, there's a complex plane involving imaginary numbers, but for simplicity, we will stay analyzing the horizontal axis. Now, when k matches the frequency, the points stop spreading out and instead cluster on one side. This results in the center of mass of all these points shifting dramatically to the right. This happens because the rotation cancels out the signal's oscillation. Additionally, if we have a more complex signal here, made up of a signal with a frequency of 2 and 5, we can see how the Fourier theory works. If we advance k, it has a match at 2, and then the center of mass stays 0 until it gets to 5 again, which are the two components making up the signal. We can verify that no other value will alter the center of mass. As k increases, the samples are rotated more quickly around the circle. When the rotation speed matches the signal's frequency, the points align and cluster together, producing a large result. When it doesn't match, the points spread out and cancel. The Fourier theorem works because sine and cosine functions are orthogonal. Orthogonality refers to perpendicularity, meaning where two vectors, functions, or data structures meet at a 90-degree angle. Since sine and cosine functions are orthogonal, the integral, which is a way of adding up infinitely many tiny pieces to get a total sum, of any two different sine or cosine functions will be 0. This means that each frequency contributes something unique to a complex signal which cannot be replicated by any other frequency. The Fourier series takes advantage of this because frequencies may be isolated. Thank you for listening to my project video on my Medium ISP, the Fast Fourier Transform Spectrum Analyzer. Although I couldn't present you a final product today, I hope you learned something new, and I hope you have a good day. Thank you.